Okay, hi everyone. Good afternoon. My name is David Smith, and I'm joined by Lokesh Khanna. And it's our pleasure and privilege to speak with you today. In this session, we're going to review a collection of architectural best practices that we've collected over the years that will help ensure the high availability of IP MPLS networks. And I'll also add that we've seen firsthand network outages that could have been prevented had these best practices been deployed. Okay? So a little bit of background about us. I've been with Cisco with 30 years. I live outside of New York City. And for the past 25 years, I've been supporting large-scale IP MPLS networks.
Good afternoon, everyone. My name is Lokesh Khanna, and I live in Denver, Colorado. I've been with Cisco since last 10 years, and I've been supporting hyperscalers and service providers since last 25 years.
Now, we have a lot of material to cover, so we will take questions at the end of the session, and we'll try to leave time for that. There is also and we'll stay as long as it takes, as long as you want us to answer questions in the room or outside the hallway. And there is also a WebEx room where you can post questions all week, and we will respond to them as quickly as possible. Okay? We've also included our email addresses on the previous slide. And so at any point this week or in the future, if you have any questions and want to discuss any of these topics in more detail, please don't hesitate to reach out. Okay? And in the session, we estimate there's about 40 different best practices that we will review. In the session file, we've included additional best practices, right, as reference slides in the session file. We won't cover those in today's session, but we included them for your reference, and we're focusing on the ones that we think are most important and most relevant. Okay? Okay. All right, so here's our agenda and the different categories of topics that we'll cover. You know, these topics may seem a bit old school, but we believe these are more relevant now than ever, given the essential role that the internet and wide area networks play in today's world. This session will focus on architectural best practices, but obviously operational best practices are equally important, but those are outside the scope of this session. However, one of our peers on Wednesday will be presenting. He's hosting a session and will present a complementary session focused on operational best practices. So if your schedules permit, we'd recommend you check that as well. Okay? All right, so let's begin. Network redundancy. Most modern networks have multiple layers of redundancy deployed today, right, to eliminate single points of failure. Right? This includes at the facility's infrastructure layer, as well as at the optical layer, and of course, the IP layer. Right? And this includes redundancy both in the forwarding plane as well as the control plane. Okay? But why is it then, there's a delay here. There's a delay with this clicker. Excuse me. Maybe I'm too far. All right. Why is it then, despite multiple layers of redundancy, that network outages still happen, right? Despite this redundancy, right? And that's because redundancy works very well when components fail, when they fail hard and fast. Okay? But when components simply malfunction or misbehave, the consequences can be devastating despite redundancy. Okay? And so, how do we ensure the high availability of networks and ensure compliance with defined SLOs and SLAs? Well, we need to mitigate the many different forms of both hardware failures as well as soft failures. And we also need to mitigate or address minor issues timely before they become major issues or major outages, okay? And so how is it that a relatively minor issue could become a major outage? Well, that's because of this concept called the critical state. Okay? The critical state is when a complex system, such as a network, is operating at a tipping point, and any minor disruption or issue could trigger a system-wide failure. Okay? And so this concept of the critical state is often or best represented by what's called the sandpile model. And in the sandpile model, random grains of sand, one by one, are dropped on a tabletop, right? Sand pile forms, and at some point, and it depends on the state of the sand pile, the next drop grain of sand will either be harmless or trigger an avalanche. Okay? So how do we prevent our networks from getting into this critical state? Well, it's through the combination of architectural best practices, including network redundancy, IP control plane best practices, IP forwarding best practices, and reducing network complexity.
All right. We all know that network redundancy provides protection against single point of failure, link failure, node failure, path failure. But what happens when you have multiple failures, which partitions your IP network, which makes it unusable? Implementing IP control plane, data plane best practices is still our first line of defense, but there is another layer of defense, multi-plane network architecture. Multi-plane architecture means different things to different people. Here we have included a few examples of multi-plane architecture. Topology 1 is the same as we showed earlier, which is a single physical plane and single logical plane with single IGP. Topology 2 is same single physical plane, but now we have sliced it and we have created two logical planes, but we are still using single IGP. Topology 3 is another flavor of multi-plane architecture, where now we have added more routers. We have created two physical topologies. We have created two logical topologies, and also we have created interplane links between two for possible fallback. Topology 4 is same as topology 3. However, we have taken out the interplane link for full isolation. 2, 3, and 4 are using single IGP, if you noticed. Topology 5, on the other hand, has two physical, two logical, and now we have created two separate IGPs, one per plane. So if there is any IGP failure in one plane, it will not have any impact in the second plane. Let's take a look at some of the deployment models for multi-plane architecture. You can use it as active backup, where your red plane can act as active, blue plane can act as backup. You can also do load balancing, traffic sharing. You can do active-active. You can steer VPN traffic through red plane and internet traffic through blue plane. You can run secure traffic through one plane and unsecure to other. You can also make use of one plane as if you want to upgrade that one plane. You can put traffic on the other plane and upgrade the red plane while traffic is riding on the blue plane. So there are multiple deployment models, multiple use cases. Obvious question is, how do we make use of this plane and how do we steer the traffic? A couple of technologies available. You can play with IGP cost, BGP policies, RSVPTEs. We highly recommend making use of SRTE policies and SR Flex Algo because of its simplicity, scalability, and advanced capabilities. Now let's take a look at node redundancy as well. Router architecture comes in 3 flavors. We have distributed, centralized, and fixed chassis. Distributed and centralized, they both comes with dual RP, multiple fabric cards, system controller, multiple power supplies, and fans. So it kinds of provide you full redundancy. The fixed, on the other hand, don't come with dual RP. So they provide, but they have power supplies, multiple power supply and multiple fans. So they give you partial redundancy. From scaling point of view, distributed, you scale vertically. However, centralized and fixed, you can scale horizontally. Since distributed supports more number of ports, higher throughput, blast rate is higher than as compared to centralized and fixed. Each one of these support IP control plane and data plane best practices. Just keep in mind, fixed chassis don't have dual RP. They come with single RP, so NSR can't be supported. We'll talk about NSR later. You may also consider a hybrid model, which can be more optimal for your environment based on your availability, scale, and cost. So you can put distributed chassis, for example, in the core, and fixed or centralized or combination of 2 on the ingress side as an edge for service scaling. Let's talk about IP control plane best practices quickly. We'll begin with BGP. We highly recommend that you do not redistribute BGP routes into IGP. It's not needed. If you don't do it correctly, it can result in IGP failure, routing loops. We also recommend that you have BGP-free core. There is no need to carry BGP routes in the core. You should always make use of classic MPLS, SR-MPLS, SRv6 for your service traffic. BGP error handling, very important, another critical feature. What happens when a router receives BGP update with malformed attributes or unknown attributes? iOS XR has basic error handling enabled by default. What it means is if router receives, iOS XR router receives an update with malformed attribute, it's gonna withdraw that prefix. You also have attribute filtering capability available. Attribute filtering capability comes handy when you want to take your own action on certain attribute values. For example, as on today, deprecated attributes. There are no rules defined what to do with deprecated attributes. You can set your own rules. You can say, hey, I want to discard those attributes. When you say you want to discard it, it really means you still want to accept the prefix, but router will discard the attribute, still accept the prefix. Or you can say, hey, I want to withdraw it. I don't want to even accept it. If I have it installed, I want it to be withdrawn. I also don't want to accept it. So you can set your own actions based on your own requirements. iOS XR also supports extended BGP error handling capabilities. However, those are not enabled by default. We highly recommend that you enable those capabilities as shown in the below box via those CLIs. If you don't enable it, and if any of those 4 parameters which I've defined at the top, next hop length is not 0, for example, if you receive an update with the next hop length not 0, for example, BGP session will get reset. So it's important that you enable it on your devices. Another BGP very important feature, BGP peer max prefixes. It allows us to set the limit on number of prefixes which a router should receive from a peer. It's highly recommended that you make use of this feature, especially if you're pairing with untrusted peer, who can flood, send you more internet, more routes to your device, which more than what your device can handle. You have an option. iOS XR supports setting 3 different actions: restart sessions, syslog, or discard extra prefixes. We highly recommend that you set the last 2. For example, you can generate the syslog message, and also discard extra prefixes. If you happen to be running older code, 7.2 or before that, just keep in mind that BGP peer max prefix limit per address family is enabled by default. And the default action is reset the session. It will bring down the session if max limit is hit. So our recommendation is, A, don't rely on default values or default action. Set your own limit, set your own action. Another important feature is BGP session authentication TCP AO. I think we all have been using MD5 for our session authentication. We highly recommend that you switch to TCP AO, which is more secure and flexible. It gives you ability to change your keys dynamically without resetting the session. So we highly recommend that you make use of TCP AO for your BGP session authentication. Another best practice is BGP prefix origin validation based on RPKI. RPKI is a certificate-based global database which is pushed by these regional internet registries, RIPE, LN, APNIC, AFRINIC, and etc. And once they publish their database, you will install a validator which will pull those information, and your router will go and check with the validator whenever router receives an update. Is it a valid update, or is it an invalid update, or is it an unknown update? And based on that, router will decide whether I should accept this, I should make use of this prefix, or I should not make use of this prefix in my best path calculation. Now, these regional entities, you as a prefix owner or AS owner, as you know, you might know that these entities would issue IP addresses and AS number to you guys. So you as a prefix owner or AS owner would have to go and update these databases. For example, if you received IP addresses from APNIC, you go and work in APNIC portal, and you simply specify, hey, this is my prefix, I'm going to advertise it, and I'm going to advertise it with this AS number. So you as a prefix owner, AS owner, has to let these entities know, and they will then certify it, publish the data to the validator. Keep in mind, this feature ensures that prefix is getting originated from a valid AS number. It's not looking at the full AS path, it's only looking at whether prefix is getting originated from the valid AS number. It's also very important that when you are updating these entities, one of these entities, we call it ROAs, when you are creating those entries, make sure ROAs, you are updating them as well, as and when there are changes. If you happen to receive, for example, 2/16 blocks from one of these entities, and you plan to only use 1/16 for internet advertisement purpose, not the second one, it's highly recommended that when you are creating the ROAs, you tag second/16 with AS0. So in other words, whatever block is given to you, make sure you update these databases with those entries. Whatever you say you're going to advertise, you make sure you advertise. If you're not going to advertise, flag it with AS0 so that there is no chance of prefix hijacking. So this feature would make sure that there is no BGP prefix hijacking happening, there is no prefix misannouncements happening. I mentioned that this feature is only looking at the origin. There is some work going on where we're going to look at full AS path and see if it is valid or not. IOSXR, some work is going on as we speak, and I'm hoping sometime next year it would be available.
Okay. So BGP, of course, is vital to network stability. And with that said, BGP route reflectors, when deployed, are vital to BGP control plane stability, right? And of course, route reflector redundancy is required to eliminate single points of failure within the BGP control plane. But excessive route reflector redundancy can actually be a detriment. okay? And that's because with an excessive number of route reflectors, it increases the number of iBGP sessions, BGP update processing, and BGP paths carried on all the clients within the cluster, right? And as an example, if we look at the illustration in the top right of the slide, right, we see two route reflector clusters, right? Cluster A and B. Okay? They're identical, except for cluster B has a third route reflector. Right? Now, if we assume in this example that the route reflectors are advertising the same 1 million routes, right, then the clients in cluster A will each carry 2 million paths, right? But the clients in cluster B will carry 3 million paths, right? So that's 50% more paths, 50% more sessions, and update packets and update packet processing with just that one incremental route reflector, redundant route reflector, right? And these numbers scale linearly as you increase the number of BGP route reflectors within the cluster, okay? Further, as you increase the number of route reflectors within the cluster, it can also delay BGP convergence, right? Because a client, it can't withdraw a route that is no longer available until it receives withdraws from all of its route reflectors, okay? And so it could potentially delay BGP or degrade BGP convergence. And so the recommendation is to deploy no more than 3 route reflectors within a cluster. And it's also recommended to keep the route reflector clusters relatively small in order to manage the blast radius, right, to an acceptable level in the event of a route reflector cluster failure. Okay? All right. So in large-scale BGP networks, they may require multiple BGP route reflector clusters, right, to scale the control plane, right, to either scale the control plane, provide fault tolerance, such as geo-redundancy, or to optimize BGP routing, okay? And so in general, there are 3 different design options for a multi-cluster route reflector architecture. Those include full mesh, multi-tier, and multi-plane. Okay? So in the next few slides, they each have their pros and cons, and in the next few slides, we'll walk through those. Right? So here we show a full mesh multi-cluster design. Right? And so in this illustration, we have 3 clusters, each with a pair of route reflectors. Okay, my pointer's not working. Cluster A, B, and C. And as you can see, as the slide title implies, there's a full mesh between all of the route reflectors in all of the clusters. Okay? So this is a widely deployed model. It scales well. But the limiting factor is manageability, right? Because every time you add another route reflector or route reflector cluster, you have to touch every other route reflector in every other cluster to add IBGP sessions, right? So that is the primary limiting factor of this design, but it's widely deployed and scales otherwise, okay? The second design option is a multi-tier route reflector cluster design, right? And so in this design, rather than have a full mesh between all of the clusters, cluster A, B, and C in this example, those route reflectors in the 3 clusters become, say, they operate at tier 2 level, right, within the architecture. And then this design adds a tier 1 level of route reflectors, right? And so now all of the tier 2 route reflectors, they peer, instead of a full mesh between each of them, they peer with the tier 1 route reflectors, right? So this design reduces the mesh between all of the tier 1 clusters, right? So it helps with scaling the control plane, right? However, the drawback is it could degrade BGP convergence because now BGP updates between clusters, have to propagate through additional hops in the control plane, right? Through the tier 1 route reflectors, right? And then further, in the event of a tier 1 cluster failure, the blast radius could be significant, right? So those are some of the pros and cons of this architecture. The third design option is a multiplane architecture, okay? And so in this design, there's only a single tier of route reflectors, right? Same 3 clusters as earlier, clusters A, B, and C, but now we divide or partition each of the route reflectors in those clusters into separate independent planes, right? In this example, we show a dual plane design, a red plane and a blue plane. So in the red plane, in each plane, right, the route reflectors in each plane have a full mesh to one another. So all the route reflectors in the red plane peer with one another, and all the route reflectors in the blue plane peer with one another. So it's less of a mesh compared to the full mesh, right? However, it's subject to multi-failure events. And so in this example, we show a double failure. So if, for example, there's a route reflector node failure in one cluster, cluster A in this example, and at the same time, there's a route reflector node failure or session failure in the blue plane, in the other plane, say in cluster C, that would break connectivity between the clients in cluster A and the clients in cluster C, okay? And so for that reason, in a multi-plane architecture, we would always recommend 3 planes, okay? So those are the differences between the different multi-cluster route reflector designs. The optimal design depends on the topology and network scale, ultimately. Okay. So another route reflector best practice is to isolate slow peers or slow clients, isolate them from faster peers or faster clients, right? And so what I mean by a slow peer or a slow client is typically a legacy router that has less control plane resources than the modern routers, right? And the issue with slow peers is that if they can't keep up, right, they will throttle the route reflector, which will then delay updates to faster clients within the update group, right? So a single slow peer will slow BGP convergence for all the clients in the cluster, okay? And so for that reason, it's recommended that they be isolated. Now in XR 731, we introduced a capability that could automatically detect and isolate slow peers, and it was enabled by default. But this version of the feature consumed significant CPU. And so it's been deprecated, right? And not recommended. But if you're running a later version, in 791, we introduced a new version or implementation of this feature. Provides the same behavior, identifies and automatically isolates slow peers outside into their own update group. This, again, was introduced in 791. This consumes minimal CPU, and so it is recommended, but this is not enabled by default, right? And so if you're running a more recent version of software, we would recommend this feature. However, if you're unable to enable it, you can manually isolate slow peers into their own update group, right, by statically configuring them, right? And then there's show commands. Using show commands or Yang telemetry, you can identify the slow peers manually and then configure them in their own update group, right? And again, in doing so, you don't delay BGP convergence, for the other clients in the cluster. Okay? So several other route reflector best practices are listed here. First, we recommend that separate route reflectors be deployed per address family. Right? This provides better service scaling, and it provides better fault isolation. Okay? And one good example is the BGPLS address family, for example. Right? BGPLS, it's not directly involved in BGP best path computation, and so we recommend putting it in its own route reflector so it doesn't degrade best path computation for the other address families. Okay? Secondly, we recommend the use of BGP add paths, right? Because by default, a route reflector will only compute and advertise a single best path. Right? And so that can lead to potentially suboptimal routing, or in some specific scenarios, it could lead to route oscillations, as documented in RFC 3345. Okay? And so BGP add paths mitigates those issues. Right? But if you're unable to enable it, an alternate option is BGP optimal route reflection. Right? With BGP ORR, the route reflector computes the best path not based on its view of the topology, but based on the view of select clients within the cluster. Okay? And then lastly, BGP route target constraint is also recommended for the layer 3 VPN or EVPN address families because it reduces the volume of BGP updates sent from the route reflector to the clients and ultimately the BGP update processing on the clients. So with RTC, the clients will only receive routes of interest, right? They won't receive routes that they don't want and which they'll ultimately drop, okay? So it's a waste of control plane processing and a waste of bandwidth within the network.
All right, we spoke about centralized and distributed chassis with dual RP. What happens when active RP fails? That's when NSR comes into picture. We highly recommend that you enable this feature for your IGP, for your BGP and LDP. Once enabled, your standby RP would synchronize itself with the primary RP. We'll make sure that it has all the session information. So when primary RP fails, it would automatically take over. It doesn't need to signal the peers to say, hey, I'm going to go down. And traffic will not be impacted at all. One important thing, as called out in the last bullet point, is that standby RP must be in the ready state for RP failover to work. So our recommendation is that you monitor the state of standby RP as well in your network, which can be done via syslog messages and things like that. And just keep an eye so that when you need it, it's available for you. NSF is another important and very old feature, which we highly recommend that you should use it. NSF provide protections against process restart events. For example, iOS XR, every process would have its own some resource limit assigned to it. What happens when you hit that limit due to any bug or any reason? iOS XR has self-healing capabilities. When our limit is hit, iOS XR will automatically restart that process. Obviously, we don't want traffic to be impacted because of that. Once you have NSF enabled and you have GR-capable devices, in this picture, for example, R2, which is running OSPF, would send the Grace LSAs to its peering node and notify them, hey, I'm going to go down before process restart happens. Now, peers know that, okay, this device is going to go down. Peer would take an action on that, would retain the OSPF route in its fib, will not delete those routes. R2, on the other hand, would also do the similar thing, would retain the routes which it has learned from the peering devices, OSPF routes. So in other words, with this feature, when you have traffic flowing, it will not be, there will be no impact on the traffic when the process restart is taking place on R2. Let's take a look at IGP best practices now. We mentioned that do not redistribute PGP into IGP. It can cause issue. But what if someone accidentally does that? Human error, or it can happen. Max redistribution prefix limit, or the CLI, would allow you to give you protection against such accidental configuration. By default, iOS XR has a limit of 10,000, warning at 75%. We highly recommend, again, do not rely on the default value, adjust the values based on your own requirements. This CLI is available for both OSPF and ISIS. If you're running OSPF, the max LSA command, which is another layer of defense, would be very beneficial. So we recommend that you should use that CLI as well, where you can limit the number of LSAs device can receive. Especially when you're doing redistribution, those LSAs would appear as non-self-generated LSAs. From 7.10 onwards, there is a max external LSA CLI added. So you can make use of that CLI and set the limit. Again, do not rely on default values. 791 has a default max LSA value of 500K. Set it based on your own requirement. ISIS, obviously max LSA is not applicable to ISIS in this case. ISIS has other mechanism built in, which restricts the number of LSPs to 256.
So we also recommend enabling IGP cryptographic authentication. Not only does it protect against security attacks against the IGP, but it also protects against operators or connectivity errors, specifically the collapsing of two independent IGP domains. Right? And we mentioned this, this connectivity issue. I know it's a kind of a niche scenario, but we mention it because we've seen it. We've seen this occur in a production network which caused a network outage. Okay? And what happens here is, as you see in the illustration, there's two independent IGP domains, right? They are connected by two border routers, R1 and R2, okay? And those two border routers are running two instances of ISIS, right? This scenario applies equally to both ISIS and OSPF. And in the event an interface in R1 that's configured in instance 1 is accidentally connected to an interface on R2 configured for instance 2, right? If that connectivity error occurs, it will collapse the two domains into one, right? Doubling the IGP control plane scale in each domain and potentially causing the control plane to fail. Okay? And so cryptographic authentication would protect against this scenario as well, okay? Provided each domain has its own unique encryption key. And so we mentioned this because we've seen it in production. We've seen it happen in a production network, okay? Now, before we go on to the next slide, if you noticed, or the next best practice, you'll notice that all of the routers here are operating in level 1, level 2 routing process type, okay? And because that is the default behavior in iOS XR. And so the recommendation, and this is specific to ISIS, is to only use IS type level 1, level 2 on ABR routers, okay? Don't rely on the default. Only use that routing type mode or process type mode on ABRs, right? And so level 2 backbone routers or level 1 area routers should be configured in level 1 only or level 2 only, respectively. Okay? Because in the previous illustration, cryptographic authentication would have mitigated that connectivity error, but also if the routers were configured in level 1 only, even without cryptographic authentication, those adjacencies wouldn't have been formed, right? And the two IGP domains, the control plane of each IGP domain wouldn't have collapsed into one. Okay? Okay. Another best practice specific to ISIS is to not configure multiple area addresses within a single ISIS instance, right? Because in doing so, once again, you can potentially collapse multiple areas into one, right? Once again, doubling the ISIS control plane and potentially breaking the ISIS control plane if you exceed scale limits, right? And so this, similarly, we see this type of scenario happen most often when customers are migrating from OSPF to ISIS, right? And this happens because, because of the differences in the way ISIS and OSPF handle areas, right? So again, with ISIS, when you configure multiple areas on a node, it makes those areas synonymous, right? And so they're collapsed into one, right? In OSPF, and that's because in ISIS, it associates areas with nodes, not interfaces. In OSPF, conversely, OSPF associates areas with interfaces, right? And so a single ABR, a single OSPF ABR can support multiple areas, multiple independent areas, which is not the case with ISIS. ISIS requires dedicated ABRs for each area, okay? So if you're looking at migrating from OSPF to ISIS in the future, just beware of this difference. Okay. Now, just as BGP is critical to network stability, so is the IGP, right? And in modern networks, with modern routers, the IGP can scale in excess of over 1,000 routers per area, okay? But if you need to scale beyond that, or if you want to reduce the blast radius of your IGP, then there are multiple well-known and proven techniques to do so, right? And those are listed here, right? The use of hierarchical IGP with multiple areas, or the use of multiple IGP instances, and using either BGP-LU, an SRPCE, or IPv6 summary routes to provide connectivity between PE loopbacks in different domains. Or, alternatively, a multi-plane architecture with each plane having its own IGP, right? So these are all options to reduce the blast radius of an IGP. Here we highlight some high availability best practices for IP multicast. First and foremost, NSF and NSR also apply to PIM and IGMP. Rendezvous points, unlike BGP route reflectors, they participate in the multicast forwarding plane. They serve as the root of multicast shared trees. And so obviously redundancy is critical for rendezvous points. And in fact, for large-scale multicast networks, we recommend dedicated routers as rendezvous points, okay? In that way, if there's many multicast trees with a lot of multicast control plane activity, the multicast control plane won't adversely affect the unicast control plane, specifically on the rendezvous points. Okay? Multicast also benefits from fast IGP convergence. Okay? Because multicast trees that are affected by a failure event, they can't be rebuilt until the IGP reconverges, right? So having a fast IGP benefits multicast convergence, right? Benefits multicast traffic. Right? And so while IGP convergence, is on the order of sub-second or multi-seconds, right? Depending upon your IGP scale, there are also next-gen multicast technologies that enable 50 millisecond protection for multicast. And these are listed here on the bottom. Multicast only fast reroute, multicast LDP, point-to-multipoint, RSVPTE, ingress replication, and so forth. Okay.
All right, time to look at IP forwarding plane best practices now. Let's begin with a very simple but powerful utility, interface fault handling. iOS XR supports carrier delay utility, or CLI, with up or down value you can define. By default, iOS XR has carrier delay up as 200 millisecond, for example, for Cisco 8000 series platforms. What it means is, even if at layer 1 level interface has come up, iOS XR is going to wait for additional 200 millisecond to ensure that interface is fully up, there are no flaps during that duration, before it brings it up and let the upper layer protocol know about it, be it IGP or BGP. Carrier delay down, on the other hand, by default, iOS XR has a value of 0, which means as soon as layer 1 goes down, iOS XR will bring that interface down. So end of the day, carrier delay is used to delay the processing of link up-down event to the upper layer protocols. You may want to tweak these parameters based on your own requirement. For example, some operator may need you to set carrier delay down with a higher value instead of having 0. But if you have your own alternate path, if you have the right technology configured, FRR, we'll talk about that later, you're welcome to use carrier delay value as 0. Then traffic would switch to the alternate path within sub 50 millisecond conversions, as long as you have the right technology configured. Interface dampening is another utility which we highly recommend that you should enable it. It's not enabled by default. And it keeps an eye on, it monitors that interface is stable or not. If link is not stable, it's going to penalize that interface and keep it out from the network. Both event dampening and carrier delay are very useful in terms of reducing the noise or churn going to the control plane. If you have too many flaps on the link, too many flaps on the interfaces, that can cause churn, unnecessary noise in the control plane. So we highly recommend that you make use of both the functionalities. The next one is PFD. There are two ingredients to when we talk about getting sub 50 millisecond conversion. There are two key ingredients. One is detecting the failure as soon as it happens and notifying the upper layer protocols. And then second is having the right technology configured so that you can use that notification and fall back to the alternate path. PFD helps us detecting the failure as soon as it happens. Obviously, there are other failure detection mechanism available. For example, if you have an optical circuit, you get LOS when there is a failure on that circuit. However, it is not guaranteed, depending on that circuit and the path it is going through, it is not guaranteed that you will always receive, or router would always receive LOS. For example, in the picture shown below, if there is any outage happening on the optical path next to R2, there is a possibility that R1 will not receive LOS. So we highly recommend that you enable BFD on your optical circuit as well. It gives you another layer of defense. With BFD hardware offload, you can you can detect a failure within 12 milliseconds. The other detection mechanism is relying on the routing protocol. Let the timer expires. So OSPF, 30 seconds. BGP, 180 seconds, hold down timer. And during that window, obviously there would be traffic loss. So we don't want that to use that either. Ethernet CFM with EFD is another functionality which is available. However, BFD has more advanced capabilities. You can use BFD strict mode. You can have multi-hop BFD, single-hop BFD. So there are more advanced capabilities available in BFD. So we highly recommend that you use BFD to detect the failure so that BFD, once failure is detected, BFD can notify the upper layer protocols. If you happen to use bundle in your network, BFD comes in two flavors. You can have BFD over bundle, we call it Bob, or BFD over link bundles, BLB. If you have Bob, Bob allows you to create or establish one session, one BFD session per member. So if you have 4 members in a bundle, you would have 4 BFD sessions. With BLB, you only set up, router will only initiate or create one BFD session. With Bob, you can have aggressive timers. It supports hardware offload, so it's faster as compared to BLB. So wherever possible, make use of aggressive timers. Use Bob over BLB if it is possible.
Okay. QoS is also essential to high network availability because it helps to isolate different traffic classes and, most importantly, guarantee priority traffic. Right? And so the recommendation is, when defining your traffic class queues, is that you allocate one specifically for control plane traffic, right? BGP, OSPF, ISIS, PIM, et cetera. Right? And give it adequate bandwidth so that during congestion, the control plane traffic is never dropped, right? It's guaranteed, right? Because if control plane traffic drops, then you can lose IGP adjacencies, BGP sessions, PIM joins and so forth, which can disrupt traffic, right? Could disrupt traffic for the affected prefixes, all right? So as it relates to QoS, that's the first recommendation, but hand in hand with that is at the network edge, traffic is marked or colored properly, right? In that way, it's classified correctly and queued correctly downstream, right? And it prevents, low priority traffic, to prevent low priority traffic from being serviced from a high priority queue, or non-control plane traffic being serviced from the control plane queue, okay? And so, to ensure control plane stability in the network, which is essential to network stability, you need to avoid control plane packet drops, okay? So here we highlight some of the differences between the next gen or the modern routers versus some of the legacy or older routers, okay? And the key difference is that the available buffering on the higher speed interfaces on modern routers is less than the older routers on the lower speed interfaces, right? As illustrated here. And so the key takeaway is that you can't simply copy, say, existing QoS buffer configurations, right, from the older routers with, say, lower speed interfaces to the newer, more modern routers with higher speed interfaces, right? Because that could potentially, if you oversubscribe buffers, right, that could lead to random or indiscriminate packet drops, right? Which would potentially affect high priority traffic, potentially affect control plane traffic, okay? Similarly, there are differences. It's stuck here, I don't know. Okay, here we go. There we go. Similarly, there are differences between the modern routers and the older routers as it relates to MPLS label scale and label allocation, right? And we summarize those here. So we've always recommended that, for example, LDP labels only be allocated for host routes, say PE loopbacks, as opposed to all the prefixes in the IGP, right? And so that becomes more important on the modern routers, right? In terms of both core and edge, right? On PE, on edge nodes, running layer 3 VPNs or 6PE, the ASR 9000, for example, supported all the different label allocation modes, per prefix, per VRF, per CE, et cetera, right? On the newer, more modern routers, per VRF label allocation mode is required, okay? And then conversely, on ASBR routers that are running inter-AS option B, right? Because there is no VRF associated with option B interfaces, right? Per VRF label allocation mode doesn't apply. What's required on these newer routers is per next hop received label, right? And then similarly, on PE routers that are running IPv4 and IPv6 unicast, it's recommended to set next hop self on those routers because this and all of the other items listed here, they reduce the amount of label consumption on these platforms, right? And reducing label consumption, because labels are scarce resource, helps to mitigate the risk of out-of-resource conditions in the forwarding plane, right? And so if you hit an out-of-resource condition in the forwarding plane, it could disrupt traffic, okay? So these are the recommendations as it relates to label allocation on the various platforms. Okay. Another question or topic that comes off quite a bit is whether internet routing should be run in a VRF or the global routing table, okay? And so there's pros and cons on each side of the debate, right? And we have customers running both. Clearly, the key benefit of running internet in a VRF is that it automatically protects core routers. It automatically blocks IP reachability from external sources to core routers, right? That's the primary benefit. However, the challenges are it introduces a significant complexity, right? Especially for brownfield networks, right? So if you're thinking about migrating from internet routing in the global table to internet routing in a VRF, your edge routers potentially have to carry those internet routes twice during the migration, once in the global table and once in the internet VRF, right? Until the migration is complete, right? And that doubles the routing, the RIB and FIB scale on those platforms, okay? Also, VPN prefixes, right? They consume more scarce resources, such as the MPLS labels that we just talked about. And now your internet routes, by putting them in a VRF, you have to deal with all these classic layer 3 VPN attributes like RDs, RTs, VRF import, et cetera, right? Just additional complexity. And of course, if you're running any form of internet multicast, right, that would have to be migrated to multicast VPN, which is obviously much more complex than global IP multicast routing, okay? So there's pros and cons on each side of the debate, and ultimately, it's whatever's optimal for your networks.
All right. I briefly touched on two ingredients to get 50 millisecond convergence. One was BFD, which was to detect the failure as soon as it happens. Second one is FRR. But before we get into FRR, what happens when BFT notifies the upper layer protocol? If router has to, at that time, figure out, oops, the link is down, to get to the destination, I have to do some calculation, find the alternate path, program it in the hardware, which is a time-consuming work, which means the conversions can be in 2 to 3 seconds. You can also say that I can use aggressive timers, not recommended, rather leverage BFT. What if router already has the backup path programmed? What if there is a technology which allow you to tell the router, go and create the backup path for my IGP prefixes? That's what we're going to talk about here in FRR. To get to sub 50 millisecond convergence, you can go with RSPTE, but it requires stateful tunnels. Per prefix LFA allow you to create, pre-program the backup path for your IGP prefixes, but it doesn't guarantee that it will be able to do that in all the topologies for all the prefixes. Remote LFA is another way to achieve same result. However, it requires target LDB session with the destination boxes. TLFA, which is highly recommended, is topology independent, doesn't require any target LDB session, doesn't require any stateful tunnels, and we get sub 50 millisecond convergence using TLFA. So we highly recommend that you consider TLFA in your network. Let's take a look at how does TLFA work. To enable TLFA, we have listed the CLIs at the top. You can see there are 2 CLIs which would enable TLFA on your device. Once enabled, so in this topology, once enabled, every router for every IGP prefix would calculate an alternate loop-free path to get to the destination, which would get pre-programmed. If you don't have TLFA, let's take a look at what happens when I don't have TLFA enabled. In this topology, let's say traffic is flowing from A to C for prefix XY. There is an outage between B and C. We all know that all the routers would, once a failure has been detected, a topology change notification will go out. Each router will start looking at, will do its own calculation to find the alternate path. They don't do it in synchronization. They're not synchronized when they're doing it. So router B will do it at its own time, A will do it at its own time, D might be a little slow. So, which can result in having micro loops. So assuming A is still in the process of calculating an alternate path, B has detected the failure, B will send the traffic back to A, but A will say, hey man, to get to A XY prefix, you are still the best path. So it will send it back to B. Traffic will go in loop during that time. Same is the case with D or E or F. With TLFA enabled, as I said, backup path would be pre-programmed. It would be a loop-free path. So B is going to say, okay, for me to get to XY prefix, the loop-free path is via router F. I just need to, with segment routing TLFA enabled, I just need to insert F's segment ID. And let F know that it needs to send it via interface between F and C, so that traffic doesn't come back. So through this, we are able to now achieve sub 50 millisecond. Path is already programmed. As soon as notification comes in, hey, the link is down, BFD tells us in 12 millisecond link is down, backup path kicks in. All right. Let's also take a look at SR micro loop avoidance. You can enable it via CLIs listed at the top, right-hand side. TLFA kicks in when it sees hard failure. There was a failure between link B and C. What happens if I just change the metric on the link between B and C? Will TLFA kick in at that time? Answer is no. TLFA will, that path which TLFA created, pre-computed path which TLFA created will not kick in if there is change in metric in this case. So that's where SR micro loop avoidance comes in the picture. Once enabled, it will tell router B that as soon as there is a change in change in topology, router B at that time would start calculating alternate path a loop-free path, which will, in this case, will still be via F. So we highly recommend that you enable both TLFA and SR microloop avoidance in your network. Let's quickly take a look at BGP. We spoke about what if we have the backup path pre-programmed, which was for IGP, but what about BGP? BGP PIC allows us to achieve similar thing. It allows us to get backup path programmed for a BGP learn prefix. BGP PIC comes in two flavors. We have PIC edge node protection. We'll talk about that first. So with PIC edge node protection, as soon as ingress PE router, which is PE1 in this case, detects a failure of egress PE, which is PE3 in this case, PE1 would switch to the alternate path. So moment I enable my BGP PIC, every node in this topology would program a backup path for BGP prefixes. As soon as egress PE goes down, PE1 via IGP will get notified that, okay, PE3 is no longer available, or loopback of PE3 is no longer available. PE1 will switch. So ingress PE would switch the traffic, in that case, for destination XY. The next one is BGP PIC edge link protection. Both flavor of PIC, in principle, would program the backup path. So in this case, when I have an outage between my PE3 link and CE link, an egress PE and the CE link, the traffic switching will happen on PE3. Moment I say BGP PIC is enabled, PE3 would have the backup path programmed for prefix XY and say it's going to be available via IBGP path via PE4. So in this case, the traffic switching will happen on egress PE itself via IBGP path through PE4. Both flavor of PIC assures that convergence would be in sub-second.
Okay. Network simplification is all about reducing complexity. And reducing complexity not only makes automation easier, but it makes high availability easier because you're reducing the number of potential failure scenarios. Okay? So in a simplified network, we would recommend the following technologies. Right? Multi-protocol BGP as the unified service overlay control plane for all network services. Segment routing as the unified forwarding plane for all network services. Segment routing traffic engineering for advanced control of traffic flows. Centralized SDN controller, or SRPCE, for network-wide orchestration of SRTE policies and network bandwidth. BGPLS to signal topology information and traffic engineering information to the centralized controller. BFD, as Lokesh talked about earlier, for fast failure detection. DiffServ QoS, as I talked about earlier, to isolate different traffic classes and guarantee priority traffic. And then Yang model-driven telemetry for programmability, management, and automation. And then lastly, routed optical networking for better network efficiencies, right? As well as better network economics. Okay? Now, in this next slide here, oops, okay, we show the protocol stack of a classic IP MPLS network on the left and the protocol stack of a simplified network. Okay? So at the top layer of the classic IP MPLS protocol stack, you see both multi-protocol BGP and LDP, right? BGP for internet and layer 3 VPN services, and LDP for layer 2 VPN services, the targeted LDP sessions that are used by VPLS or VPWS, right? In a simplified network, you can eliminate LDP, those targeted LDP sessions, through the use of EVPN, which is another address family within BGP, right? But it's not just another address family within BGP. It provides, advanced capabilities, active-active load balancing, for example, faster convergence, that are not available with classic VPLS or VPWS, okay? At the transport layer, on top of the IGP, you'll see in a classic IP MPLS network, LDP for label forwarding, RSVPTE for traffic engineering or fast reroute, and then BGP labeled unicast for scaling the IGP using unified or seamless MPLS, right? Well, in a simplified network based on segment routing, you can eliminate LDP, RSVPTE, and BGP-LU, right? Segment the IGP, ISIS, with SR extensions can provide all of those capabilities and beyond, okay? And then lastly, in the forwarding plane, we can eliminate MPLS labels entirely with the use of SRv6, right? And so, classic IP MPLS, it encapsulates transit packets with the MPLS label stack. SRv6 is simply encapsulating transit packets with an IPv6 header, right? SRv6 is IPv6 routing, okay? And so as you can see, the protocol stack can be greatly simplified with BGP and segment routing, and specifically SRv6. Okay? Now, SRv6, it's not just about mass network simplification. It also provides mass network scaling and advanced capabilities not available using other technologies, full stop. And so we'd recommend, I know there's a number of segment routing sessions this week. We'd recommend, if your schedule permits, to check those out. Okay? So in summary, as Lokesh and I talked about at the onset of the session, we've seen network outages that could have been prevented had many of these best practices been deployed. And so we recommend deploying as many as applicable and as feasible to help ensure the high availability of your networks. Okay? Please complete the session survey. We would welcome your feedback. And we thank you for attending the session. Thank you for attending Cisco Live, and thank you for being Cisco customers. And at this point, we'd be happy to answer any questions you may have. Thank you.